Hello everyone, welcome back to Altium Academy. I'm your host, Zach Peterson. Today we're going to be talking about a type of routing that is sometimes used in RF boards and used to route into connectors, and it is sometimes called skip layer routing. Now the PCB world doesn't have a specific name for this type of routing, and when I use the term skip layer routing, it shouldn't be confused with skip layer vias in HDI stackups, and it shouldn't be confused with skip layer routing used in packaged substrates. But we're going to discuss this type of routing because it came up in a conversation on LinkedIn and I got a request to do a video about it. So let's go ahead and hop in and get started. Now the topic in this video is all about clearing ground below certain PCB traces that require impedance control in PCB routing. And I want to run over when are some typical instances that you might do it and what are the effects on signal integrity. Now this all came up from a conversation on LinkedIn and I have that conversation pulled up right here. Let's take a look at this post from Troy Hopkins, one of my brothers in PCEA. Here he's talking about a routing strategy called welling down. And what is welling down? Well, I'll leave folks out there in the audience to read through this entire post, but what I want to do is just take a look at this image. Here you can see we have an image attached to this post, and in this image we have three different objects that are being routed in a PCB. First, we have a digital trace at 50 ohms. You can see here that it is situated over a ground plane on layer 2. And of course, because it has the shortest distance to the trace, that trace is going to be very narrow. Then you can see here we have an RF line with the same impedance at 50 ohms. It is referenced to ground on layer 3. And so because the distance is much larger, the trace width is also larger. Here you can also see that we have an RF trace at the same impedance of 50 ohms, and it is referenced to ground on layer 3. So because there is a larger distance between the trace and ground, then we also have a larger width for this trace in order to hit that 50 ohm target. Here on the right, we also have an SMT pad for an RF component, and you can see that the pad is naturally much larger. The reason that the pad is larger is because, of course, you're probably going to mount a component there, but also because it is also referenced to ground, but the ground is at a deeper distance inside the stackup down on layer 4. So basically this section of pad is being treated like a transmission line that also needs to be matched to 50 ohm impedance. Now some years ago I heard that this type of routing strategy was called skip layer routing, and that is because you basically skip a layer when you reference ground for that impedance controlled line. And I was told that by somebody who works on satellites. And this is not to be confused with skip layer routing in packaged substrates, as you can see here in my comment on the post. And then here you can see Venkata Krishnan writes, "Hey Zach, can you please explain this in a short video on the YouTube channel? It would be very helpful for us." So I think the first thing to address is, why would we want to do this? Why do we want to pull off ground below a trace that has impedance control in some instances? Troy actually does give an explanation in his post when he looks at the RF trace that has the larger trace width. And folks out there in the audience who are familiar with signal integrity and with RF transmission line impedance and losses will know that this wider trace has a smaller skin resistance. So basically this reduces the additional AC resistance that's caused by the skin effect. So if you reduce that skin resistance or that additional AC resistance from that skin effect, it reduces the total insertion loss that you would expect on that interconnect. So essentially this technique allows you to pick up some additional insertion loss margin over a long route at high frequencies. Maybe you routed the trace as a narrow trace over a long distance and you found that you're hitting your insertion loss limit early. You can then get back some of that insertion loss margin by widening out the trace midway through the route, and as you widen out that trace, you then just clear out the ground below that trace in order to ensure that you have the same impedance everywhere along that transmission line. The other reason that you might want to do this is also alluded to in this post, but Troy doesn't state the reason specifically. So here you can see that he says he often uses this with antenna launches and RF signal paths. So an antenna launch can go into an antenna directly, or it can come off of a connector, like for example a coax connector. And that's this instance where you have the RF SMT pad here in the right hand side of this image. For example, if this pad is being used to mount a connector for an antenna, this pad is going to be very large, and you might have a 50 ohm trace that's routing into this SMT pad. Well, this pad being much larger, because it needs to be larger to mount a component, it means that if you just keep the ground on layer 2 or 3, the impedance of this pad is going to be lower than the impedance of the transmission line, and that could add to the return loss on that interconnect. But if you clear out a little bit more ground into a deeper layer, that then ensures that this pad also looks like a 50 ohm transmission line. That helps ensure the impedance match between the incoming feed line and the pad and the component that's being mounted on that pad, and helps to minimize return loss. Now, if you're actually going to do this, how do you set this up in the design rules inside your CAD tool? Well, what we're going to do now is take a look inside of Altium Designer, and I'll show you how to set up the impedance calculation and the design rules, and some way that you can use to check that the rules are consistent in both sections of the route. So here I am inside of Altium Designer, and I'm in a blank PCB, and I've created a very generic 6-layer stackup just to illustrate how to use the impedance tool to implement the calculation for skip layer or welling down routing. So here inside the impedance tab, the first thing we need to do is to create an impedance profile. Now, what you need to do is determine which layers you're going to be routing on. So for example, you might have a feed line coming in on layer 1. It then is referenced to ground on layer 2. But then when you're implementing skip layer routing, you may want to reference it down to, for example, layer 3 or 4. First, we're going to do the basic calculation with a reference to layer 2. And the key here is this bottom ref entry. So this drop-down tells you where your ground plane for this trace is located. And here, by default, it's selected as layer 2. And then you can see here the calculation has automatically filled in the required trace width. It tells you that the impedance is exactly 50 ohms, and then it gives you some other information here in the properties panel. So this is the first calculation that we need to successfully implement skip layer routing without creating DRC errors. So that involves calculating the impedance with layer 2 as the reference. So a good idea at this point is to put in, for example, 50-L2 in the description to indicate that this is a 50 ohm line with layer 2 as the reference. Then what we can do is create another impedance profile, and this impedance profile is going to also be 50 ohms, but instead we're going to use layer 4 as the reference. So I'm naming it 50-L4. Then what I do is I go over here to the bottom reference dropdown, and instead of selecting 2, I just select layer 4. There you go. You can see that it is now referenced to layer 4, and it calculates that the required width is 74.455 mil. So what that means is that along the length of this route, this trace is going to have to fan out from 10.68 mil all the way out to 74.455 mil. Now, 74.455 mil trace is not very practical when you're trying to transition from a 10 mil trace with reference on layer 2. So instead of referencing all the way down to layer 4, we might instead just reference down to layer 3. And that gives us a trace width of 31.572 mil. So that's a much cleaner transition between a 10 mil trace and a 30 mil trace. And we do this just by selecting, again, this layer 3 in the bottom ref dropdown. I also want to make sure I change my impedance profile so that the description matches the reference layer that I'm actually using. So now that we've set up our width calculations for these RF lines, how do we enforce those widths in the routing tool inside the PCB layout? Well, we can do that in the design rules. And if I just go into the design rules, you'll see here that there is a routing width rule. And by default, there is this generic routing width rule right here. Now, how do we enforce that in the PCB layout? Well, what we need to do is go back into the PCB doc file, open up the PCB rules and constraints editor, and then you'll see here that we have a routing width rule that we want to use. And we want to apply that routing width rule to our RF nets in our design. Now, there's a couple of different ways to apply these two different rules to the same RF interconnect in the design. And I think you can do it a couple of different ways. One way is to create two different RF nets with our different widths and then connect them together with a net tie. So here in this scope, we would then want to apply this to the different nets that we set up in the schematic. And to do that, we would just use the net scope option. We would then select net number 1 in this dropdown. And then for the other impedance profile, we would still use the net scope, but then we would select the other net in this dropdown. And that allows us to use the two impedance profiles that we calculated in the stackup manager. The other way to do this is to just use a single RF net that applies across the entire RF interconnect. And instead of using a net tie, we can then use the minimum, preferred, and maximum width values inside of a PCB design rule that applies only to that RF net. So here we would just create one rule. We would then select net as the object scope, and then we would select our RF net from the dropdown. Then we could program in our preferred width and our maximum width values for that net. And that will allow that trace to vary between the 10 mil width that we calculated for reference on layer 2 and the 30 mil width that we calculated for reference on layer 3. So this would be the ideal way to do things if you were going to fan out the trace in the middle of an RF net in order to recover some insertion loss margin. Now here's an example of what this might look like if you're routing from a trace into a large component pad, which is the other case that Troy mentioned in his post. Let's take a look here at our RF power module design. So this RF power module design, you can see here, it has a trace on the top layer, and this trace on the top layer has a width of, as I recall, about 8 mils. You can actually see it's 7.764 mils. And then we're routing into a connector. So this is a large SMA connector, and that SMA connector requires this very wide pad up here on the top layer. So when this trace routes into this pad also needs to be at a 50 ohm impedance. And in order to do that, you can see here that some ground has been cleared in the internal layers, and the reference for that pin is on the bottom layer of this PCB. Now here in this approach, we can just use a single design rule with that RF net using the impedance profile that we set up in the stackup manager. If I just go into the rules editor, you'll see here that I have a width RF rule, and you can see I'm using the custom query in net class RF. This then applies the impedance profile only to the nets in that net class, and you can see here it fills in the minimum, preferred, and maximum width automatically. Now this rule is going to enforce this trace width as you route all of the traces between the components in this RF interconnect. Now the last thing that I want to bring up is the transition between these two elements in the PCB. So here we're going from a narrow trace to a wide connector. And I think it's natural to ask, do we need to place a taper in this design between this trace and this pad? Well, theoretically, you shouldn't need to, but it's always worth checking if you have some simulation capability. So when you have simulation capabilities, you can place a taper and you can compare the return loss with the taper versus without the taper. Now for this specific design, we actually did this in a video from a couple of years ago. And if you go take a look at the link in the video description, you'll see where we actually compared the case with the taper to the case without the taper. And we found that this design actually functioned just a little bit better when we didn't use the taper in this layout. Now that's not going to be the case for every PCB. In some cases you might do the simulation and you might find that you need to have a taper in between this large pad and the narrow trace in order to bring your insertion loss down sufficiently low within the frequency range that you're targeting. Of course, Simbeor is a great tool for that, but there are other simulation tools you can use as well. Ansys HFSS is another great tool that you can use to do that simulation if you have the budget. Also, openEMS is capable of doing that simulation, and openEMS is an open source software. Now the next question is, how do you design a taper if you determine that you actually need one? Well, that's another topic that we've looked at in another video. And if you go ahead and take a look at the links in the video description, you will find a link to our taper design video. And we look at a couple of examples in that video targeting frequency ranges that are pretty similar to what we used in this example project. Thanks for watching this video, everybody, and of course, thanks for all the great comments and questions. And if you have questions or comments, make sure to leave them in the comment section. Of course, make sure to check out those other design videos in the video description. And last but not least, don't forget to call your fabricator, folks. We'll see you next time.